So in this video we're going to look at how the gradient can give us the direction of maximum or minimum change for a function, and we're going to look at some other things that the gradient vector can tell us. The gradient, it turns out, is very useful. So one of the things that we've done is we've defined the directional derivative in terms of the dot product of the gradient of f dotted with u hat, where u hat is the direction in which you want to know the derivative. And we're going to be able to establish some concrete results from having defined the directional derivative using the dot product of the gradient and u hat. So the first thing we want to do is recall from our homework on dot products that we discovered that the cosine of theta, where theta is the angle formed by two vectors, the cosine of theta is just the dot product of u and v divided by the size of u and times the size of v. So what we can do is look at our gradient vector. Here's gradient of f, and here's u hat. And we know that gradient of f and u hat as two vectors will have some angle theta between them, and we can calculate the cosine of that angle. So the cosine of the angle between the gradient and u hat is just going to be based on this formula that we previously developed. It's going to be the gradient of f dotted with u hat divided by the size of the gradient vector times the size of u hat. And then what we want to remember is u hat is a unit vector. It's a vector of length 1. That's what it means to be a unit vector. So the size of a unit vector is just 1. So I don't even need that down there, because 1 times the size of the gradient will just be the size of the gradient. And then if I multiply both sides by the size of the gradient vector, I discover that the gradient of f dot u hat is just the size of the gradient vector times the cosine of the angle formed by the gradient vector in u hat. So that allows me to come up with another way of calculating the directional derivative. Take the size of the gradient and multiply by the cosine of the angle formed by the gradient vector and u hat. And this definition is particularly interesting because it allows me to ask some questions like, when is the directional derivative the biggest it can be, the smallest it can be? When is the directional derivative going to be 0? And I can get that information from this way of defining the directional derivative. And that's why it's useful to have different ways of defining things, because different formulations of the same thing can give us different insights into that thing. So in this case, we know that the directional derivative of f can be found by taking the gradient of f and multiplying it by the cosine of the angle formed by f and u hat. So I can say, when will this be max? When will the directional derivative in the direction of u be max? Well, the size of the gradient vector is always positive. The size of a vector is a positive number. So this product will be maximum when the cosine of theta is at its maximum. And the cosine of theta runs from -1 to 1. So the cosine of theta, the biggest it can be, is 1. And 1 times the size of the gradient is just the size of the gradient. So the biggest the directional derivative ever gets is the size of the gradient. And when will that happen? Well, the cosine of theta equals 1 when theta equals 0 degrees. So that tells us that the gradient vector here, gradient of f, and u hat have to have an angle of 0 degrees between them. Well, that only happens when the two vectors are parallel and in the same direction. In other words, the angle between them is 0 degrees. That means that the gradient of f is biggest when it's pointing in the direction you're interested in. This tells us that the gradient of f itself is the direction of maximum change. So the size of the gradient is the biggest the rate of change ever gets, and the greatest rate of change occurs in the direction of the gradient vector. Then we can ask, when is the directional derivative at a minimum? When is it the smallest it can be? And again, we get that directly from the cosine function. The cosine function is the smallest it can be when it's -1. And so -1 times the size of the gradient will be the smallest value the directional derivative can ever be. The opposite of the size of the gradient is the smallest value the directional derivative will ever be. And when will that happen? Well, the cosine of 180 degrees equals -1. So when the gradient vector, grad f, makes a 180 degree angle with u hat, we have the smallest possible value of the directional derivative. That means that we have to be facing the opposite direction of the gradient vector. So the opposite of the gradient will be pointing, so if we negate the gradient, then the opposite of the gradient would be pointing in the same direction as u hat if u hat is pointing 180 degrees out from the gradient vector. So the direction of minimum change, or the smallest value the derivative can take on, will be the opposite of the gradient of f. And then we can ask the question, when will the directional derivative be 0? When will the rate of change be 0? What direction do we need to be moving in for that to happen? And again, that's going to happen. The rate of change is going, stupid pen. There we go. The rate of change is going to be 0 when the cosine of theta equals 0. 0 times the gradient will be 0. So the directional derivative will always be 0 when the cosine of theta is 0. So if here's the gradient vector, grad f, or del f, then either u hat needs to be at an angle of 90 degrees because the cosine of 90 degrees is 0, or it needs to be at 270 degrees because the cosine of 270 degrees is 0. In other words, the gradient of f needs to be hitting u hat at a right angle. So we know that if the gradient vector hits u hat at a right angle, then if we move in the direction of u hat, the rate of change is going to be 0 anytime we have u hat being perpendicular to the gradient vector. So these are three big results, right? Hey, how do you move in the direction of maximum change? How do you move in the direction of minimum change? How do you move in the direction of no change? And the gradient vector gives us that information. So the gradient vector also gives us some additional information that's pretty nice. So I can say, hey, look at the level curves of a function. So we looked at constructing level curves in a previous video and say, how is the gradient of f related to the level curves of a surface, right? And remember, we calculated level surfaces by picking constant values for our output. So we would say let z equal c, where c was some constant. So maybe c was equal to 7 or c was equal to 3. And then we cut the surface f with the plane z equals c. We looked at the trace of the surface in the plane z equals c, and then we cast the shadow of that trace down into the xy plane and used it as a 2D representation of a three-dimensional surface. So the idea is, for any level surface, the value of the level surface as you move around it is a constant, right? And we calculated, or we determined the pictures of the level curves by taking the function f of xy and setting that function equal to a constant. So if you're moving in the direction along a level curve, the function always has a constant value. So if I let u hat represent direction of motion along a level curve, then the directional derivative in the direction of u hat along my function f, as I move along the level curve, the derivative has to be 0. Why does it have to be 0? Because as I move on the level curve, the function's equal to a constant, which means it's not changing, and the derivative of a constant is 0. But we saw already that we can calculate the directional derivative by taking the dot product of the gradient with our direction vector u hat. So now I have the dot product of two vectors having to equal 0. And this is where the properties from the dot product homework come into play. If the dot products of two vectors are if the dot product, of two vectors is 0, singular, then the two vectors are perpendicular to each other. The dot product of perpendicular vectors is 0. If the dot product is 0, the vectors are perpendicular. It's an if and only if type of a statement. So now I can figure out how the gradient of f is related to a level curve, because if you move along any curve, as you move along the curve, your direction of motion is always tangent to the curve. So as I move along this level curve here, my direction of motion is either tangent in this direction or tangent to the curve in this direction, depending on which way I'm walking. Am I rotating counterclockwise or clockwise around the curve? So I'm going to have my u hat, my unit vector in the direction of motion, will always be tangent to the curve. And if u hat is always tangent to the curve, gradient of f is always going to be perpendicular to u hat. But if the gradient is perpendicular to a tangent vector, then the gradient is also perpendicular to the curve itself. So the gradient of f at any point you are along a level curve in the xy plane, the gradient of f will always hit that curve at a right angle. And we know that the gradient function tells you how to move in the direction of maximum change. So for example, if I go right here and I draw a point, and I say, hey, these level curves get larger in value as we move outwards, then here's something I would know. I would know that the direction of maximum change would be to move perpendicular to the level curve. And that's going to intersect this next level curve at some point, and then to continue to move in the direction of maximum change, I would move perpendicular to the level curve. You get to here, keep moving perpendicular to the level curve, move perpendicular to the level curve, move perpendicular to the level curve in the direction of the gradient. Actually lets you draw in the path that you would take to have maximum change, or move in the opposite direction to follow the path of minimum change. So a key result is the gradient of f is always perpendicular to level curves. And we can kind of summarize these key results right here. This is a summary of the key points we've just gone through. The maximum rate of change at any point AB that you can plug into f of xy at any ordered pair is going to be the size of the gradient function evaluated at AB. That tells you the maximum possible change, and the gradient vector gives you the direction in which that largest change occurs. The size of minimum change is always going to be the opposite of the size of the gradient vector, and you'll always move in the opposite direction of the gradient vector if you want to move in the direction of minimum change. And anytime you move perpendicular to the gradient vector, you're moving in a direction where the rate of change is 0. And anytime the gradient is the gradient of f is always going to be orthogonal or perpendicular to the level curves of f at any given point. So those are 4 big things, and we're going to discover as we move along that we can use these results to find things, for example, like tangent planes.